Okay, our next example is the rod cutting problem. Suppose that the prices of pieces of steel rods are given to you in a table like this. So for a rod of length 1 inch, the price is 1 real. For a rod of length 2, the price is 5 reals, and so on. So now the question is, if you are given a rod of a certain length, can you determine how that rod can be cut such that you make the maximum amount of money? That is, you maximize your revenue. Obviously, this problem is not trivial, as you can see from this example. If you have a piece of length 4, in that case, it is better to break it into 2 pieces of length 2 inches each, so that you get 10 reals, rather than selling it as it is with a length of 4. In that case, you will only get 9 real. But if you look at length 3, for example, selling it as it is much better actually, because you will get 8 reals. If you are to break it, for example, into 2 and 1, then your total revenue will only be 6 reals. In fact, if you break it into 3, 1, 1 each, then your total revenue is going to be only 3 reals. So this is the issue. If you are given a length, a piece of rod of a certain length, how do you break it? Or do you even need to break it at all, such that you obtain the maximum revenue? Okay, so in terms of input and output, okay, by the way, there's an assumption here. We're going to assume for this simple example that the cutting is for free. Okay, so there is no expenses incurred because of cutting the piece. We are also going to assume that the cutting is done based on integer values. So we don't have, for example, 1.5 and so on. The rods are cut according to whole numbers or integer values. Okay, so in terms of input and output, we can rephrase the question like this. Given a length n and a table of prices pi for I from 1 to n, find the maximum revenue obtainable for rods whose length sums to n, computed as the sum of the prices of the individual rods. Yeah. So in other words, how do you break this n to get the maximum revenue? This is what we are going to solve using dynamic programming. Yeah. One note here is, if Pn, that the price for the length in total without breaking, if it is large enough, an optimal solution might require no cuts at all. If you break it, actually, you will not get the optimal solution. So it is possible to leave the rod as it is without cutting. The objective is to maximize the revenue. That may involve cutting or no cutting at all. Okay, now the first step in solving a problem using DP is to characterize the structure of an optimal solution. So we need to try to come up with a formula for the optimal solution. Now, one approach to start with is by looking at all possible combination of cuts and their corresponding revenues. We observe, for example, that for a rod of length n, there are n minus 1 possible cutting points. And if there are n minus 1 possible cutting points, It means there are 2 to the power n minus 1 different ways that we can cut the rod. For example, if your rod is of length 8, then you will have 2 to the power 3 ways of cutting it, which is 8 different ways, as shown by this diagram. So you may not cut it at all, or you will have 1 and 3, 1 inch and 3 inch, 2, 2, and so on. So one approach you may adopt is to actually look at all the possible combinations and see which one will give you the maximum. Of course, you may have more than one way of getting the maximum, so just choose one of them. Clearly, in this case, this seems to be the best because it will give you 10. This is 9, 9, 9. This is 7, this is 7, this is 7, and this is terrible, only 4. Yeah, so this is the optimal solution. Yeah, so for a rod of length 4, the maximum revenue you can get, as you can see from these figures, is 10. But we need to find a way of generalizing this for any particular length. This is basically what the first step in DP involves, finding a formula to generate the optimal solution for any given length. So let Ri be the maximum revenue for a rod of length I. Then the question is, how do we come up with an algorithm for finding Ri? A natural first step is to start by inspection with small values of I, as we have done here in this table. Obviously, for length 1, there is nothing to cut. For length 2, you will be worse off if you cut, because keeping it as it is, you will have 5, and dividing it will only give you 1 plus 1, which is 2. So no cuts. What about length 3? Again, keeping it as it is, as we already discussed, is better. But for length 4, again, as we discussed, it's better to cut it into 2 of 2 inches each. For length 5, it is better to cut it, and you will have 2 pieces of length 2, which is will give you 5, plus a piece of length 3, which will give you 8, so that if you add up, you get 13. But for a length 6, again, it's better not to cut it. This 17 is the maximum you're gonna get, and so on and so forth. So you can do an inspection and see how can you arrive at the optimal solution. Okay, but this is not what we want actually. We want a general formula that can allow us to obtain the optimal solution automatically. Perhaps the easiest way to start is by looking at all the possible options. So for each length, let us see all the possible options as we saw in the case of length 4. Comparing each of them, we will see which one will give us the optimal value. So if you like, for a rod of length n, we can define the revenue Rn, the optimal value for n, which is called Rn, by taking the maximum of all the possible options. These are Pn, this is the price for length n, this means without making any cut, or R1 plus Rn minus 1. This means cutting at length 1. Okay, so we're going to get the price for that plus the rest. Okay, or cutting at second point, so inch 2 and the rest, which will be Rn minus 2, and so on and so forth until we reach Rn minus 1 plus R1. So basically, these are the list of all possibilities of cutting the rod. Obviously, if you're going to compare all of them and take the maximum, you surely will get the maximum. But this, so this is the formula. Rn will be the maximum of all the possible combinations. Pn, or R1 plus Rn minus 1, R2 plus Rn minus 2, and so on. Now, since we do not know ahead of time which value of I will give us the maximum, we have to consider all the possible options before we determine which one will give us the maximum. This may sound like brute force algorithm, and in fact it is brute force algorithm, and therefore not efficient. But as we shall see, the process of DP will be used to improve on this algorithm and make it more efficient. So we should think of this as just a step towards coming up with a better solution. Okay, now we note that to solve a problem of size n, we solve a problem of size less than n. So see here, for Rn, we are computing R1, Rn minus 1, and so on. None of these R's is up to n. What does that mean? It means that the problem involves dividing into subproblems, which are of smaller size. This is one of the major requirements for you to be able to apply DP. The problem must be solvable in terms of subproblems. Similarly, this characterization does involve overlapping subproblems, which is another DP requirement. For example, R1 is needed more than one time, as you can see even in this expression. And the same thing for Rn minus 1, Rn minus 1. So the problems are overlapping. The second point to note is that the overall optimal solution incorporates optimal solution to the two related subproblems, maximizing revenue for each of them, for each of the two pieces. Okay, so optimal solution involve optimal solution to the subproblems. I will explain what this means by an example. If, for example, you take n equal to 7, then one of the optimal solution will make a cut at 3, giving you two pieces of length 3 and 4. Now, the optimal solution for the one of length 4 involves cutting the piece of length 4 into two pieces, which, if you recall, will give you 5 reals each for a total of 10 reals. Okay, so now this optimal solution for the length of 4 is being used in the optimal solution for the length of 7. So if you have this kind of situation where the optimal solution for a problem involves the optimal solution for the subproblems, then the problem is said to exhibit what is called optimal substructure. This is another requirement for you to be able to apply dynamic programming. So we have mentioned 3 things so far. One is you should be able to break the problem into subproblems. In this case, we are able to. 2, the subproblems should be overlapping. Yes, they are overlapping because we're going to be repeating each one of them many times for each particular call. And the third one is the optimal solution you generated should involve optimal solution to subproblems. Again, it is. So this our characterization is applicable to DP. In other words, DP can be used to improve this characterization. However, even though our characterization will work fine, there is actually a simpler way to decompose the problem. Okay, we notice that every optimal solution that we find, it will have a leftmost cut. In other words, there is some cut that will give the first piece of length I, say, and then the remaining piece of length n minus I to the right. So the first cut of length I to the left, and the remainder, which will be of length n minus I. If we think about it, any optimal solution we get is going to be of this form. Good. So if we think of it this way, then we are actually reducing the problem into just one subproblem. Because the first part, the left one, no need to cut it any further. Only the right hand side we need to cut. So in that way, we have only one subproblem to deal with, not two as in the characterization we have here. Here we have always R1 and another R. Okay, R2 and Rn minus 2. So, and we have to solve each of them separately. But here, we are saying the first part doesn't need any more solution. We can obtain its price directly because it doesn't need to be cut anymore. It is the leftmost cut. Okay, so the price for that is already known. It's Pi. It is only the right hand side that we need to solve. Okay, so this leaves only one subproblem to solve rather than two subproblems, and therefore it is a better characterization than the first one. Okay, the solution with no cuts will have its first piece, the one on the left, to actually be the whole length, I to be equal to n. And the revenue for that, of course, will be Pn. In that case, the remainder on the right hand side will be of length 0. And we'll have an imaginary revenue of 0. So with this idea, we can recharacterize our solution to this form. So Rn will simply be the maximum of Pi plus Rn minus I for I from 1 to n. Because the idea is the first part is not going to be cut anymore. So we know its price. Just look for it from the table. It's going to be Pi. We only need to solve for the right hand side. So this is a better characterization than the first one. And it is also having all the properties required for applying dynamic programming. So this is the one we are going to adopt. Now the next step, having characterized our optimal solution, is to come up with a recursive algorithm to solve it. This is what we are going to see next. Okay, we have here a routine called cut road, a recursive routine cut road that will take two inputs, the table of the prices for the different lengths, and the n. So we have a rod of size of length n, and we want to know its optimal revenue. Okay, so this is the algorithm. It first checks if n is 0, obviously there is no revenue, so we'll return 0. Otherwise, we simply use a loop to find the maximum. So we are actually checking all the possible values here. So we have to vary I from 1 until n, compute the value of Pi and Rn minus 1, this one by making a recursive call with a smaller size, and compare it with the previous results. If you get a bigger value, you're going to take the new one. Otherwise, you take the former one. Basically, you're trying to find the maximum. This is essentially what this algorithm is doing. So it initializes a variable q, which will be used to obtain the max, to minus infinity. And then in a loop for I from 1 to n, we compute pi. So this is just reading the price from the table, the price for length I, and making a recursive call with n minus I. Assuming the recursive call will give us a value, so we're going to go add up and compare that result with the current value of q. Of course, initially current value is minus infinity. Which one is bigger? So we assign the bigger one back to q, and then repeat the loop, okay, for the next value of I. Okay, so compute again for the next value of I, and the next one will be I equal to 2. Compare it with the previous value of q and update your maximum. So at the end of this loop, q will have been the maximum revenue. Just return it. This is basically the recursive top-down. How good is it? Obviously terrible. This procedure works, but it is terribly inefficient. According to the book, if you code it and run it with a length of 40, it may take about an hour to compute. The running time doubles for each increase in n. Okay, why is it so inefficient? Again, like the Fibonacci, is because of the incredible number of repetitions involved. Here is a recursive tree showing you the recursive calls involved for n equal to 4, for example. Okay, so for n equal to 4, as you can see here, to find for R4, you have to compute for P1 plus R3, you have to compute for P2 plus R2, you have to compute for P3 and R1, and P4 and R0, and then take the maximum. So suppose we represent this as a tree. So calling for 4 will involve calling for 3, as you can see, calling for 2, calling with 1, and calling with 0. Now when you come to compute the call with 3, it involves calling with 2, calling with 1, calling with 0. Okay, as you can see here. So it's very similar to the tree that we got with the Fibonacci sequence. There are many repetitions. Yeah, so it says there are lots of repeated subproblems. It solves the problem of size 2 twice. It solved the problem of size 1 4 times. And it solved the problem of size 0 8 times. Now this is just for length equal to 4. You can see if you count the number of zeros, 1, 2, 3, 4, 5, 6, 7, 8. The number of 1 is 4. 1, 2, 3, 4. The number of 2 is 1, 2, and so on. So imagine this n is not 4 but 40. How many zeros are you going to have? How many 1s? How many 2s, and so on? Okay, so essentially this algorithm, the running time is exponential, just like the Fibonacci. Okay, this is the running time formula. If you try to compute it, you will see that you're going to get 2 to the power n. So we know we are going to get this anyway. but we did this as a step to solving it using DP. So that's what we're going to do next. How can we now solve this, or how can we improve this using dynamic programming technique? Okay, so how can we improve this using dynamic programming solution? Obviously, as we have been saying, instead of solving the subproblems repeatedly, we're going to use a table to be storing previous solutions, so that once we solve a subproblem, we're going to save it in that table, and next time we need it, we just read it from the table. Okay, so solve the solution to a subproblem, or save the solution to a subproblem in a table, and refer back to the table whenever we revisit the same subproblem. In other words, the general term in DP is store, don't recompute. This is a classical trade-off between time and space. We're going to use space to save our previous solutions, so that we save time. We don't have to recompute them, and therefore we are saving time. Okay, this approach can turn an exponential time solution into a polynomial time solution, as we already saw with the Fibonacci example, and as we're going to see with this rod cutting problem. Okay, so again, as we saw with the Fibonacci sequence, there are two approaches: top-down with memoization and bottom-up. We're going to look at the top-down approach first in this case, because it's the one that is very similar to the recursive algorithm that we just seen. So just modify the algorithm so that it uses a table to save the result, and that will give you the memoized version. Okay, so we're going to solve recursively in this memoized top-down version, but we will be storing the results in the table, as I said. To find a solution to a subproblem, first we look into the table. If the answer is there, use it. Otherwise, compute the solution to the subproblem and then store it in the table so that you can use it, the same result, in the future. This is the meaning of the term memoization, remembering what had been computed previously. Okay, in the next slide, we're going to see the actual memoized version of the algorithm. All right, so like we saw with the Fibonacci, the procedure is again divided into two parts. The first part, just initialize the table. So here is the memoized cut rod routine. It's gonna receive two inputs: the price table P and the length N. Okay, the first thing it does is it creates an array. It creates an array of size 0 to n, because we're going to have R0, R1, R2, and so on until Rn. And then in a loop, it will initialize all the cells to -infinity. This is all it does. Create an array, initialize it to -infinity. In -infinity here, because we are finding maximum, so initialize with the smallest value, so that if we encounter a bigger value later, we're going to update this. So if we see -infinity in a cell, it means the value was not computed before. So once we initialize the array, we pass it to the second routine, which is called memoized cut rod auxiliary. We pass the array R along with the table of prices, and our n. And this is the memoized cut rod auxiliary. As you can see, the first thing it does, and this is very important, if it comes in with n and the array, it first check, is the value at Rn greater or equal to 0? If it is, terminate the recursion immediately and return the value in that array. So no recursive call will be done if the value was computed earlier. Okay, if it is not computed earlier, then we proceed as normal. Initialize, I will check for the base case. If n is 0, obviously q is going to be 0, and we just return the q. Of course, because the revenue of a rod of length 0 is 0. Otherwise, we proceed as before. We initialize q to minus infinity, and then we use a loop that runs from 1 to n, each time computing a new value and comparing it with the current q and updating q with the maximum. However, we notice here that in making this recursive call with n minus I, as I mentioned earlier, it will check first if a value for that particular n is there. It doesn't need to do a recursive call, it will just return it. So although this looks very similar to the recursive version, actually it is much better. So after computing the q, again, don't just return it. No, save it in the array in position n before returning the q. This is basically the memoized version of the routine. Now let's look at the bottom-up approach. In the bottom-up approach, as we saw in the Fibonacci sequence, the idea is to sort the subproblems by size and solve the smaller sizes first. That way, when solving a subproblem with bigger size, we will have already solved all the smaller size that we need, and therefore we just read them from the array. So this is the bottom-up version. It receives again the table of prices and the n. It initializes the array, or rather it creates an array and start with r at 0. R at 0 is 0. Then it runs into a loop for j from 1 to n, because we have to compute for each of the cells of that array. But for each value of j, we're going to find the maximum by computing all the possibilities, or by comparing the revenue for all the possible cuts. So we need an inner loop here for I from 1 to j. Okay, it's very similar to our formula. If n is 1, we only need to go from 1 to 1. If it is 2, then we're going to go from 1 to 2, and so on. So depending on the outer loop here, the value of j, we will run the inner loop from 1 to that. What do we do inside the loop? We're going to be computing pi and r at j minus 1. Now here, please note, r at j minus I is already computed. It's in the array. So we are only reading it, adding the pi to get the revenue for that particular cut, and comparing with q. Take the maximum, update q with the maximum, and go back and try again. So at the end of this inner loop, we will have known the optimal value for I. Alright, so that optimal value actually is the optimal value for j. Okay, I should have said at the end of this inner loop, we will have obtained the optimal value for j. It is this that we need to store in our array at position j. So you see rj stores the optimal value before we now return it. So this is how the bottom-up approach works. It simply means starting with the smaller values and saving them in the array, so that when we come to the bigger values, we just read the values from the array. So what is the running time for this algorithm, the bottom up and the top down? For both of them, actually the running time is theta of n squared. It is obvious, of course, for the bottom up approach, because there is a nested loop there. Okay, so this will go n times, and in the worst case, the inner loop will also go n times. So overall, you're going to have n squared. Okay, so that's what we are saying here. For the bottom up, doubly nested loops are involved. Therefore, number of iterations for the inner loop will the number of iterations for the inner loop will form an arithmetic series, which in the worst case will be n squared. For the top down, the memoized cut rod solves each subproblem just once. Okay, so we have n cases because we're going to have 0 to n subproblems. However, to solve a problem of size n, there is a loop needed. So the for loop will iterate n times over all recursive calls. So the total number of iterations will form again an arithmetic series. And therefore, even in this case, the running time is going to be theta of n squared. Now, another approach to determining the running time of these algorithms is to use what is called subproblem graphs. Yeah, and the subproblem graph is a directed graph in which one vertex is used for each distinct subproblem, and an edge or a directed edge is used if computing an optimal solution to a subproblem directly require knowing an optimal solution for the subproblem y. Okay, if to compute x, you need to know the value of y, then you will have a directed edge from x to y. For example, for the red cutting problem with n equal to 4, this is going to be our subproblem graph. So obviously for a problem of size 4, we need to know the problem of size 3. Okay, it needs the problem of size 2, it needs the problem of size 1, and a problem of size 0. Similarly, for a problem of size 3, we need that of 2, that of 1, that of 0, and so on. So this is called a subproblem graph. We can think of subproblem graphs as a collapsed version of the tree or the recursive tree for the particular algorithm, where all nodes for the same subproblem can be collapsed into a single vertex, and all edges can go from parent to child. Subproblem graphs can help to determine the running time. Because we solve each subproblem just once, running time will be the sum of times needed to solve each subproblem. The time needed to compute a solution to a subproblem is typically linear in terms of the out degree for that vertex. And the number of subproblems will be equal to the number of vertices. Therefore, the running time for the whole algorithm, provided these two conditions holds, is going to be linear in terms of the number of vertices and the number of ages together. That will give you the running time for the whole algorithm. This is the idea of using subproblem graphs to determine the efficiency of algorithms. Now the final step in DP algorithm design is to reconstruct a solution to the problem. So far we have focused on computing the values of the optimal solution rather than the choices that will produce that optimal solution. We now extend the bottom-up approach, the algorithm that we developed for the bottom-up approach, to record not only the optimal values, but also the optimal choices. We're going to save these optimal choices in a separate array. Then we use a separate procedure to print the optimal choices. This is the idea. Having found that the revenue for a particular length is a certain amount, the question is which cuts give you that amount. So this is the extended bottom-up cut road routine. It receives the same parameters, the table of prices and the n. However, here it initializes two arrays, R and S. R is going to be used to store the optimal revenues for a particular n, but S is a new array. It's going to be used to store the particular point where we make the cut in order to obtain the optimal revenue. Right. So as before, R0 is initialized to 0. The outer loop goes for j from 1 to n, because we have to compute for each possible value of n. We initialize our variable that we use to find the maximum revenue, that is, as minus infinity. Again, no change here. The inner loop for the particular value of j will go again from 1, for I from 1 to j, no change. The change is here. After we compute a particular value for the current value of I, if that I turn out to give us a better value than our previous Q, then not only do we update the maximum Q to be that new value, but we also save this I in our array S at this particular J. So not only are we obtaining and saving the maximum revenue, but we are also saving the value of I that gives us that optimal revenue. Okay, so after the loop, of course, we're going to update Q to also be in the, we're going to save after the loop, the inner loop, that is, we're going to update the revenue for J to be equal to Q. Now at the end of the nested loop, we're going to return both the array R and the array S. This is the algorithm. Yeah, so it saves the first cut made in an optimal solution for a problem of size I in the position S at I. To see what all this means, let us now take our example in more detail to show how the RIs and the SIs are computed. So RI are the revenue for this particular length, and SIs are going to be the point where the cut was made to obtain the optimal revenue. Okay, so let's start remembering that this is our general formula. Rn is the maximum of PIs plus Rn minus 1 for I from 1 to n. So if you take R1 R1. Okay, so your n is 1, meaning this summation will go from 1 to 1. I will vary from 1, so basically there is just one value, which is P of 1 and R of 1 minus 0, which is R0. So what is P of 1? The price for length 1 is obviously 1. Price for length 0 is revenue for 0, of course, is 0. So R0 is always 0. So therefore, the only value we have for this particular one is the one itself. Okay. Now, what is the point at which we got that is when I is equal to 1. So S1 will be 1. So that's why here we are saving both Ri and Si to be 1 and 1. Okay, let's take the next value of n, which is 2. So suppose n is 2. So if n is 2, then our maximum here will compare two values for I from 1 to 2. So P1 plus R1 and P2 plus R0. Notice the P will be increasing, but the R will be decreasing. Okay, so P will run from 1 to 2. Okay, because we are looking at 2 is as our n. So from 1 to n means from 1 to 2. So P will vary from 1 to 2. But R will vary from will be decreasing by 1 each time, because it's n minus 1. Okay, so if n is 2, 2 minus 1 will be 1 the first time. Then when n becomes, when I becomes 2, the R becomes 2 minus 2, which is 0. So these are the two possibilities we have to check and find the maximum. Now, what is P1 for us plus R1? P1 is clearly 1. And R1, we just computed it in the last time. It is 1 as well. So 1 plus 1 is going to be 2. Okay. What about the next term? P2. P2, we computed it earlier. P2 is 5. And R0 is always 0. So 5 plus 0 is 5. The question is, which of these is the maximum? Obviously, 5 is maximum. This is why we highlight it here as blue. Therefore, our R2 is 5. And that's what we saved here in this location. Which cut give us this 5? It is this value of I. So when I is 2, that is when we get the maximum, not when I is 1. Therefore, our S2 is 2. Okay. Next one, for n equal to 3, we have 3 possibilities. P1 plus R1, P2 plus R1, and P3 plus R0. When n is equal to 3, we have 3 possibilities. P1 plus R2, P2 plus R1, and P3 plus R0. And again, we can compute these values directly from the table. P1 obviously is 1, and R2, we just computed it earlier, it is 5. So that will give us 6. 1 plus 5 is 6. P2 is 5, and R1 was 1. So again, 5 plus 1 is 6. And the last value is just the P3 plus R0. Well, R0 is always 0. So we're just going to get 8. The maximum here is 8. So this is our maximum for maximum revenue for n equal to 3. At what point do we get this 8? Is when our I is equal to 3. So our S3 therefore is 3. Okay, so this you can continue. Is the same idea basically for the rest of the cells. So for n equal to 4, we're going to have 4 possibilities which you can compute like that. You will observe that when you are computing these values, the p's will be going from left to right, and the r's will be moving from right to left. And you just need to be adding both of them to get the next term. So for example, P1 R3 is P1 and R3. Then P2 and R2. P2 R2. And then finally P3 R1. P3 R1. The last one is always P4, the next P plus 0. So this is an easy way to compute it if you are doing it manually. And you need to be able to know how to do this actually, because this is what you will see in an exam or a quiz. You will be given a table like this to find the values of Ri's and Rj's. Okay, these are the remaining values for n equal to 5, n equal to 6, n equal to 7, n equal to 8, n equal to 9, and n equal to 10. Okay, so this is our solution from our extended bottom-up cut routine. We now have the two arrays, Ri and Sj's. The final thing we're going to do is reconstruct the solution. If we are giving any n, can we tell not only the revenue that we're going to get, the optimal revenue, but also the cuts that we're going to make? Okay, to do that, we need another routine that will do the printing. It is called print cut road solution. So the print cut road solution will call the extended bottom-up cut routines. Will call the extended bottom cut road routine, sending it the same P and N, the P being the table of prices, N is the size, and return the two arrays, R and S. Once we have these two arrays, we can now use the i's that we have been saving in the array S to print the actual cuts that are followed to obtain the optimal revenue. And this is the loop that will print actually the cuts. So while n is greater than 0, print s at n, then update n to becomes n minus s at n. You will see what this means in a moment. So suppose, considering the same example, we call this print cut road solution with this table and with n equal to 8. So the question is, what is the optimal revenue if I have a road of length 8? Not only that, how do I cut the road in order to obtain the optimal revenue? Okay, so this is the routine that will tell us the cuts that we're going to make. So this is how this routine will execute. Of course, it will call this to get the array R and S. So assume we have this R and S. This is subpart of the table that we saw earlier. But we stop here because here the n is 8. So assuming you call this, we're going to get two arrays R and S with these values. Now, how do we know? So of course, we now know that for a road of length n, the optimal revenue is 22 reals. The question we are trying to answer now is, how did we get these 22 reals? At what point did we cut the rods to obtain these values? This is what this loop will tell us. So it starts with n equal to 8, and obviously 8 is greater than 0. So it will print s at n. S at 8 is 2. So it's going to print 2. Okay, meaning there was a cut at length 2. Then it will update n to be n minus s at n. Okay, well, n is 8 and s at 8, as you can see, is 2. So update n to becomes 8 minus 2, which is 6. Then repeat the routine again. So obviously 6 is still greater than 0. So we're now going to print s at 6. So print s at 6. So it will print 6. Alright. Then update n to be n minus s at n. Well, n is 6. And s at n is also 6. So this time if we do the subtraction, we're going to get 0. And the loop will stop. So what does this tell us? It simply tells us that for our rod of length 8, if we want to get optimal revenue, we have to cut it into 2 pieces. One of size 6 and another of size 2. Now if you look in the table, the length of size 6, the cost or the price for it is 17 real. The one of size 2, the price for it is 5 reals. If you add 5 plus 17, you're going to get 22. So this is the idea. This final step is not only telling us the revenue we're going to get, which is 22, but it is also telling us how to get it. Okay, so to get it, we have to cut the rod of length 8 into 2. One of size 2, which will give us 5 reals, and another of size 6, which will give us 17 reals. These are the 2 values that are added to actually get this 22 reals. And that brings us to the end of the lecture. As usual, I have a set of exercises for you to try to help you check whether you actually follow the lecture. The exercises are generally from the book, and the first one is saying consider a modification to the rod cutting problem in which, in addition to price pi for each rod, each cut incurs a fixed cost c. The revenue associated with a solution is now the sum of the prices of the pieces minus the cost of making the cuts. Give a dynamic programming algorithm to solve this modified problem. So basically a very minor modification to the problem we have just solved. If you recall, at some point we said we're going to assume the cutting of a rod is for free. So suppose now the cutting is not free, but each cut is constant c. How will you modify the algorithm to solve this problem? Again, using dynamic programming. Okay, the second problem says modify the modified cut rod to return not only the value but also the actual solution too. So just like we extended the bottom up to return another array s, which will give us the point where we make the cuts, we also want the memoized cut rod to be extended in the same way. Finally, Trace the execution of the extended bottom-up cut rods algorithm for n equal to 10 and the following pricing scheme. So this table is slightly different than the one we use. And now we want the solution. Is it different actually? Yeah, it is different because you can see, for example, for 6, the price was 17, and also for 7. But now the price for 6 is 19, the price for 7 is 20. So the pricing are slightly different. We want you to trace the execution to find the two arrays, Ri and Si. Okay, so after each iteration of the outer loop of the algorithm depicts the state of the array R and indicate the optimal total price and the corresponding location of the cuts. So not only do you have to run the extended button up, but actually you also have to run the print cut rods subroutine to know where do we actually make the cut to obtain the optimal solution. This brings us to the end of this lecture. Thank you very much.